Welcome to Lecture 9. So in this one we're going to be talking about linear momentum and collisions. So first off, linear in physics just refers to the variable being in a straight line. It's actually all that we've really worked up to at this point. Most everything that we have, forces go in straight lines. They might be at an angle, but we break them down into their component forms. We also have the power, energy, everything that we've seen is things moving in straight lines for the most part, right? Everything that moves along, you move a box along the floor, or the cat jumps up in the air, or any of these things can be modeled as straight lines. So the term linear means that, and they're bringing it in now because in the next couple of chapters we're going to be changing to angular, which will be rotating things. So just getting used to the terminology of linear. And linear momentum. Momentum is a term used for a mass traveling with some velocity, and we represent momentum with a lowercase p. It's of course a vector because it's equal then to whatever the mass is times whatever the velocity is. Velocity, of course, also being the vector, mass being the scalar. So if a thing has momentum, the more momentum it has means the more mass or the more speed that it carries. Right, so a lot of things refer to, well, if you can gain some momentum on this, or if you can, slow down the momentum. Okay, it means there's a large mass, a large velocity. It's either traveling fast or it's very massive. Momentum is very helpful if your mass ends up having to change, like in rockets, where you're trying to launch something off the face of the earth, and as you go up into space you burn the fuel that you're carrying and you eject it out the back in exhaust and fumes and explosions. So that mass is constantly going down while you're going up, right? So if the mass is going down, velocity is increasing, and it leads to a momentum. It's extra helpful in those kinds of problems. Now, we haven't had anything yet where the mass is changing. We're not going to have it for a little bit, but with the mass changing, it's mainly rocket science. So Physics 1, you're into rocket science. For the algebra-based class, it's really easy. You just keep things being it's linear, keep them in one dimension, just like we have been doing for the rest of this class. Everything, momentum in the x direction would just depend on velocity in the x direction, y direction, z direction. If you're in the calculus based, there's a little bit more that's involved in it. If you sum up all the forces, you will have a derivative of this mass times velocity over a derivative of time. Okay, so this is actually what Newton was saying in his laws. The F is equal to ma actually came in later, so I lied to you. Newton came up with force being a derivative of momentum with respect to time. Momentum was the main play in that part. And it would be a derivative of momentum with respect to time. That's why mass has this weird history for its definition of just going around in circles, because people were having a hard time identifying mass, and you'd say, well, mass is having to do with momentum, and then, well, no, mass has to deal with force, and they're both, they just deal with both with each other. Anyway, if you're in the calculus based, forces are the derivative of momentum with respect to time. And you can kind of see that up here. If you were to take a ddt of mv, the m could come out if it doesn't change with time. The m could come out, the d goes in, dv dt gets you back to acceleration. You'd have m times a, which of course then is force. Okay, so a couple of different ways of looking at the linear momentum equation for both algebra and calc-based. Algebra, you're just going to keep the simple. P, momentum, is equal to mv. Okay. Momentum's pretty similar to energy in the fact that if you have conserved properties, you can call it what they call it as an isolated system, right? Where all the momentum stays within the system. It is an isolated system where momentum is now conserved, which means you can take a change in momentum, which would be just mv final minus mv initial, and you'll get that equal to 0 if nothing has changed as far as momentum. Okay, so it's just like energy. If it's conserved, if there's nothing to take momentum away, then you just have momentum total is equal to 0. A change in momentum is equal to 0. Examples of this. All right, so like billiard balls, pool table, lots of different things like that, where you have objects that are free to collide, free to move. You have a collection of objects. Those objects interact with each other, but it's basically frictionless. Okay, it would technically be, you have to want it to be absolutely frictionless in order for it to be an isolated, but you can kind of get the idea that a pool table is so small that they're using it as a frictionless surface. Space travel, of course, is a much better one for momentum. Two satellites colliding, for instance, there's nothing else to stop, friction or air resistance or anything. The one satellite crashes into the other, and one carries momentum one way, one will carry momentum the other way. It might change their velocities, but the total amount of momentum, the velocity that was there, is conserved because there's nothing to slow it down. There's no friction. Another example would be gas molecules being trapped in a jar. Okay, so you'd have, let's say we have a container filled with oxygen, something like that, right? So if you have a container filled with oxygen, you'll have these oxygen molecules bouncing off each other inside of this jar, just colliding and bouncing around, and that's considered an isolated collision, right? It stays within the jar, there's nothing going on with it, it just collides and goes a different way, right? They just bounce off each other. Space travel, they're bouncing off each other, they might break each other or whatever, but they're bouncing. Pool ball, things just bouncing, colliding, but bouncing off each other and going in directions. Okay, so in that part it's similar. If you look at collisions, because that's mainly what momentum is used for, is collisions of objects. If they're bouncing off of each other and they don't lose any energy or there's no friction involved, we call it an isolated system, and momentum is conserved. If there are non-conservative properties, okay, maybe the velocity changes greatly, and there's only one mass involved, right? In that case, if the velocity changes and there's only one mass, well then the change in p is definitely not going to be 0 because you've changed the velocity of that mass for no reason, right? You need a reason that that velocity has changed. And that brings us to then the change in p is equal to this new variable I. Okay, I is known as an impulse. It's a type of collision where you get something out of the change in momentum, known as an impulse. We're going to talk about impulse a little bit more. Impulse, I'm just going to give you an equation which I will describe later on, but impulse can be written as a force times time, right? Something had to react with the system. A force had to be introduced into the system in order to get an impulse. Okay, it wasn't just two balls that went and collided. Maybe it was one ball, like a baseball bat, right? A baseball was coming in one direction. A bat came in and gave it a very large force for a very small amount of time, and the ball ended up, flying in a totally different direction. Okay, the bat gave an impulse to the baseball. It changed its momentum drastically. Large force, small amount of time. This is also what happens when you have an automobile accident. You experience an impulse, right? You experience large force, small amount of time. Okay. Another example could be the molecules of gas hitting the walls of the container. So instead of the molecules bouncing off of each other and being, just fine because they're all interacting inside, this would be the gas molecules hitting the side of the container. The container does not move, but the velocity has changed direction of the molecule. This is what's known as pressure. Okay, this is what it goes down to. It would be pressure inside of the container. It's how you measure pressure. It would be the force on the outside of the container. So anything that hits the wall or the container that does not move, okay, would be implying an impulse to it. And then, of course, a car accident here with a wall is one thing as well. Cars are designed for impact. So being you see these in your everyday life, I'll go ahead and throw a couple of these things out there. Smart car features, they have specialized chassis that have protection for the individuals inside. Okay, they're kind of built up with a cage like design in it, and it's a safety feature for you, right? It's to keep the occupants safe. So these are Formula One cars. If you follow Formula One or if you don't, it doesn't matter, they're race cars. Race cars are specifically designed, okay, to protect the inhabitant in here. The front end is missing. You can see during an accident, all sorts of things can happen to the front end. It can come flying off or whatnot. It needs to be able to protect the individuals. Same with the back end. There's no wheels. There's nothing else on here. This is one solid piece with one design in mind, and that is to protect the human that's inside of it. Now, most of you are probably not going to be hopping into a Formula One car, so you think, well, how does this affect me, right? Well, your cars, everything that you're built has a safety rating, and that is also put in mind. And there was actually a car that was designed, it was a while back, it was a few years back, by Mercedes called the Smart Car. And these got a bit of a bad rap because they were very small two-seater cars, and everybody kind of thought that they were death traps. You know, if you get into an accident with this thing, you know, there's nothing to protect you. So I actually have some footage of a crash test with this smart car. It's another YouTube video, actually. I'll put the link down in the description so you can go to it if you want. I'm just going to switch over to it here quickly so you can kind of see it. This is a smart car. Okay, it's very, very small. It's mainly plastic on the outside. Very small wheels, great gas mileage. Some of these were, I believe, I think there's batteries also installed in these. Not 100% sure on that, but you can see it's a very, very small car. But the beauty of this car is that it has a fuselage similar to the F1 car. You'll see here when it hits the wall. Okay, big collision there, right? Big collision that occurs. Car flies into a million pieces. But there is something here that remains. You see that a lot of this car gives way and lessens the impact for the driver. Okay, this car is built like a Formula One car. It has that inner cage in order to keep the occupants as safe as can be. Now, they go through a couple of things here when they look at it. Tons of plastic pieces, everything like that. And you can see here that the backside is still intact. He's looking at the roof. There's a small crease here in the roof. But you do see the seats are still there. Steering wheel has blown its airbags. And I'm not saying you would be able to walk away from this thing with no injuries. The driver's side here is pretty mangled up. But you see that it is still in one piece. So that with the wheels, the engine, the radiators, all this whole front end is all smashed apart and gone. That was designed as part of the original design on the car to keep the occupant safe. If you look at the other side of the car, door opens. The passenger side is relatively good. So the car was designed with that whole thing of protecting the occupants inside. Okay. Now, that's just one example. That's not saying that your car is designed that way. You have to look up your safety features and see how exactly your car is designed. If you want to see a Formula One accident, you should check out Romain Grosjean's crash in F1. That one's a pretty legendary crash that occurred that actually changed the design of the cars drastically as well. And normally in my usual class I go ahead and show that, but I give a warning that it is actually an automobile accident, that there is someone involved in it. I won't be doing it on here. If you want to look it up, go ahead, look it on up. It's a very interesting crash. There was a Netflix show called Drive to Survive that had pretty much an entire episode devoted to it. Anyway, these crashes lead to big impact accelerations, or G-forces. Okay, so we'll have a couple of, well, we'll probably have one example of a G-force question. It depends on how many G's of force a human can endure. So what you would do to solve that is, of course, look for the impulse. You know that the impulse, change in momentum, is equal to force times a small amount of time. So we're probably given the small amount of time that the accident occurs, and you can then find the force that was felt on the person or on the vehicle for that collision. And just for some information here, the NHTSA, for a sudden impact, it has to be a very short time. Okay, this isn't like a fighter pilot who endures, 10 G's for, seconds on maybe a minute, of it. This has to be a very sudden impact. But people can endure huge amounts of G's. So this one would cause severe injury, but about 75 G's would cause a severe injury or death for around a male, 65 G's for around a female, and around 50 G's for a child. So all of these things are taken into consideration, and that's why you have booster seats. You have car seats that are designed for this, because the child can handle less G's than an adult. All these things are taken into consideration. It's all for safety, which I think is pretty cool. Pretty cool to know that your car was designed with all of these, fancy tech things, in mind. This is also why you have more padding on your back sides and head. A lot of cars have little cup seats rather than the old cars who had bench style seats, and that's to hold your body in place during a collision. Okay, anyway, moving on. Enough about that. So here there's really only two kinds of collisions that we could look at. There's three parts, but the other two are kind of connected. So the first type of collision that we'll be looking at is an elastic collision. So in an elastic collision, the energy in the collision is completely conserved, and it's simply transferred between the objects. There's nothing lost. So the way I like to look at elastic collisions is if you took a basketball, right, and you held it up at a certain height and you let it go. The basketball would fall, it would hit the ground, and it would bounce back up. Now, if that ball bounced all the way back up right into your hands again, the exact same height, right, then no energy has been lost in that collision. You've simply let it go, it bounced, it came up, and you've caught it again. That would be known as an elastic collision, okay? Exactly the same height. I could bounce it numerous times, and it would come back to the exact same height. That's elastic. That's not what we really see in the real world, so what we see is inelastic collisions in the real world. If I let that basketball go, it will drop, it will hit the floor, and it'll come up, but it won't come back to its original height. It will have lost some of its energy. The important bit is that some of it still remains, okay? So that if you drop the ball, it comes back up, but only slightly, and you have these two objects that have collided, the ball and the ground, and they went in two different directions. The ball ended up coming down, bouncing, hitting the earth, coming back up, but it lost some energy on the way. So that's what you normally see. That's an inelastic collision. Some energy has been lost. And the nuance to that one is you can have a completely inelastic collision. Okay, so what do you think happens in the completely inelastic? It means that I take my basketball, I drop it on the floor, and it goes, and it never bounces. All right, it stays stuck to the floor. Those two masses have now combined and absorbed into now a larger mass. All right, there was no bounce at all. There was no recoil. Those two objects have now become one. All right, all that energy was just combined in. That's what's known as a completely inelastic. Okay, so if you want to think of it in other terms, instead of a baseball or instead of a basketball, elastic, you can think of pool balls bouncing off of each other, something like that. Inelastic, you can think of a car accident, two cars coming together at some speed, and one ends up kind of getting pushed out of the way, but they'll slow down, they'll roll to a stop. Completely inelastic would be a car hitting a semi or something, right, where the car is now combined, smashed together with the semi, and moving as one object. You can also think of it as railroad cars, gathering more cars in its collision. Maybe you've got a railroad car going down its track and another one coming in behind it, and it will eventually hit that first one, and they will combine and make one large mass. That's a type of collision as well. If you have lab with these, you're going to do lots of collisions too. All right, so that's the 3 types of collisions. Hopefully that's enough examples to give you an idea on what they are. And now we'll look at how to process them, how to solve them. Collisions in one dimension are generally going to be your simplest. So that's a course where we're going to start. We're going to start with one-dimensional objects, one-dimensional collisions. It's important to note the objects may touch, right? So in this case, we have 2 objects that have collided. One has applied a force on the other, and now it looks like we had a small object and a large object hit, and now they are bouncing back apart. So this actually has a touch, right? So they have collided. You might have objects like that, or you might have objects that are deflected by a non-contact force. So this could be magnets, or some type of positive negative charge, where like a proton and a helium atom come close to each other, but they're both positive, they don't like each other. They'll never actually touch, which means the one will just get deflected off of the other. Okay, they don't actually touch, but there is some repulsion in there. They don't actually come into contact. So you have those 2 types of interactions. They're both one-dimensional. Okay, even though this one's got some curvy lines, that's okay. We can think of it kind of being more of a one-dimensional. It's just the only one I could grab, only image I could grab of it. Collisions in 2 dimensions are a little bit tougher, but we've had lots of practice. We know exactly what we're going to do, right? If we have something that has an angle, you're going to have to break it down into its component form, and that's exactly what we do. So collisions that are in 2 dimensions, we break down the problem, we find out how much momentum it carried in the x, we find how much momentum it carried in the y, and then we break those down into initial and final momentums. So in this case here we have a before the collision, which is normally how we're going to draw these. We'll have a before and an after picture, so we'll have double the pictures. Okay, so before the collision, mass 1 is coming in with some velocity 1, and mass 2 looks like it's sitting stationary. So this could be 2 billiard balls. It looks like mass 1 is a little smaller, so I'm not sure what exactly that is. But mass 1 is going to collide with mass 2. It's on a trajectory where it'll hit mass 2. What is that going to cause? Well, after the collision, you see that mass 2 is now traveling with some velocity down, down lower end of the page, whereas mass 1 has also changed its trajectory, and it is now traveling at a different velocity upwards of the page. Okay, so we've got all sorts of angles. We've got a theta and a phi. Each one is going to have to be represented by its own angle. You'll break everything down into x's and y's for each of the objects, and then we'll simply tally those things up. If the total momentum changes 0, so this one momentum is conserved, then it'll be the total momentum in the initial, which is mass 1, velocity 1, mass 2, velocity 2, all initial, all in the x. Set that all equal to whatever is in the x in the final. So in the end, you have 2 masses, you have 2 velocities, they're both final, they're both in the x. You'll do the same thing for the y. Okay, set everything up in the y, initial equals final, okay, because you had final minus initial, but because it's equal to 0, you moved it over. Okay, and just keep them separate. Make sure everything on the top is in the x's, make sure this entire equation on the bottom is all in the y's, and you could solve out for any of these variables. It just depends on what's given in the problem, right? So you're going to be given a velocity, you're given a mass, you'll solve for something, okay? Whether it be the initial speed of particle 1 or the final velocity of particle 2 or whatever it is, okay? This is how you'll set them up though, all right? We look at an equality, we go, oh, everything's conserved, we need to break everything down, and we need to solve from there. So a bit more work to do it in 2 dimensions, but we'll have a practice on it. Okay, and lastly, we have our center of mass. Ooh, I see I am in the way. There, that might be a little better. We have our center of mass. So now that we've involved more than one object into our problems, and things are getting more and more complicated, that's why it's important to stay up to date on all of these. We have more objects being involved. We better talk about mass, or more importantly, what the center of it is. Okay, so here we would have maybe an irregular shaped object, or maybe 2 objects. We'll start with this one. We'll go with 2 objects. We have a mass 1 and a mass 2. Now they're different masses, but let's say they're connected. Let's say they're connected by some rod. And you're wondering, well, where would be the center of mass? If I wanted to balance these 2 masses, where would I have to place my hand in order to balance the 2, or the pivot point in order to balance the 2? Well, there's an equation for it. It's called the center of mass equation, right? And to figure out where the center of mass is on the x-axis, we simply just need to do a couple of things. I need to incorporate all of the masses, so mass 1 and mass 2, and I'm looking at how far away, so a distance, how far away that mass is from where I want to pivot it. Okay? So in here, if we just start here with, we just start on the xy axis, and I'm going to rotate around the y-axis, and I'm looking, where is the center of mass of this object? I just need to figure out a couple things. One, I need to know what the mass 1 is, and then let's find out what the x1 is. So x1 would be the distance from where I'm stating the y-axis to mass 1. So I have an x1. Okay. And then I have a second mass, so I need to add in a second mass. So I'm going to have m2 over here on the x-axis. And that's, of course, a different distance, right? Because mass 1 and mass 2 are separated, so we would have x2 being a little bit longer. Okay, so whatever x2 is, we add them up. Now, that's being just divided by the 2 masses added together, the sum of all the masses. And what this does then is that unit-wise, we have masses up top, we have masses down below. It's going to cancel out those masses and just give us the units of a distance. And that distance will be the center of its mass. Okay, so we note that with cm, the center of its mass. All right, again, if we're looking at this in an algebra-based course, it's a bit simpler. So in the algebra-based course, the equation is, of course, given to you for center of mass. You will take each individual object, and it doesn't have to be just limited to 1 or 2 or 3. It can be a whole number of objects, right? So this could go all the way out to whatever m and whatever x the number of objects is, right? So you just add up all of the objects, their mass, times the distance that they are away. So if this one, for instance, I could add another 2 balls on this side, or I could add things all over the place. You're going to add up all those masses and all of their x distances. Then divide by all of the masses. So divide by the sum of all of your masses added back up. Again, that'll cancel out all the masses, and then you'll be left with the direction. This also works in the y. Just change all the x's to y's, right? So if you want to find the y center of mass, just change the x location to a y location, right? So these happen to be lying on the x-axis, but if I were to draw one up here on the y-axis, it would now have a y height, right? It would have a y1, and then I would add up everything that's on the y-axis, divide by the total masses, and that would then give me my y center of mass. Okay. So what this is saying here is that, yep, you're going to sum up all of your masses times all of your distances and divide by the sum of all of your masses. So that's just the condensed version of what we see on the left. Okay. Or equals to, again, we're summing all of the masses, all of the x's, divided by this capital M. This capital M is just the total mass of the object. So if the object consists of M1 and M2, the total mass would be M1 plus M2. Right? So you might have, maybe you have a jar of marbles. Right? If you know the mass of each marble, and you know that there's 100 marbles, then 100 times the mass of each individual marble gives you the total mass of the entire jar. Okay, something like that is kind of where I'm going with it. Well, being that total mass doesn't change, we can pull that out, and we can have 1 over the total mass times the sum of all of its components and all of its distances. All right, so that's even a little bit long for the algebra-based. The main formula here in the beginning is basically what you need to know. If you're, if you like algebra, this is a little bit more of where you're going. You're talking about sums. If you go to calculus, it gets a little bit more, because now to find the center of mass, you want to take as small of a sample as possible. You want your mass to go to 0, right? You want the amount of mass, the change in mass, to approach 0. So you take a limit of this equation as you approach 0. And what happens when you do that? Well, you get an integral. So now you're integrating. 1 over the total mass stays outside, but you're going to integrate x as a function of mass, okay, with respect to mass. I can go over these a little bit more in the calculus-based version of the class. For algebra-based, just stick with what you already know. A great idea is a cat. Cats have a very unique center of mass that allows them to flip over while they're falling. That's why a cat usually lands on its feet. The center of the mass of the cat actually does not change while they are dropping through the air. They're just using their legs and twisting around to get motion. But we'll talk about that actually more in another chapter as well. But a large area like a cat, you'll want to break that cat down into a bunch of tiny masses and sum up over all of it, which would be an integral, okay? Which would be an integration of the cat. All right, so that's a little brief input onto center of mass. There's a couple of problems for center of mass that we'll do. It's just a good idea of knowing, now that we have more than one object, where that center of mass actually lies. All right, that's it for this one. Let's go ahead, hit the whiteboard, and we'll do some problem sets. So here we are, chapter 9. We use our first example here. So this chapter is all on momentum and the conservation of momentum. So it's a lot like the energy conservation chapter, except this time we're introduced to a new thing called momentum. And momentum is just a mass times a velocity. It's any object that is moving carries momentum with it. The larger the mass, the bigger the momentum. Larger the velocity, bigger the momentum. This usually deals with types of collisions. Now, you can think of collisions, you probably think of two things bouncing into each other, but there are also other types of collisions that you might not think of. And example 1 kind of brings that out. So here, in example 1, we have, usually with momentum, you'll have a before and an after, and that's kind of a clue on what is happening for momentum, a clue that it's a momentum problem. In the before, I have an archer. He's got an arrow, a bow and arrow, and he's ready to launch his arrow. Everything is fine, except for he is standing on some ice, and that ice is frictionless. Very, very slick ice, so I don't know, he's out hunting in the winter or something. Well, what's going to happen? I got the mass of the archer, and I've got the mass of the arrow, and you can see the arrow is much lighter than the archer. But the question here is, what's going to happen when the archer releases that arrow? Well, the arrow is obviously going to go flying by, right? So it's going at 85 meters per second, very, very fast. But what's going to happen with the archer? If they're on ice, there is going to be a little bit of backlash. Now, this is Newton's second law coming into, or Newton's third law coming into place, that for every force, there's an equal and opposite reaction. And we'll get the same thing here, that they release the bow, but in releasing the bow goes forward, the archer gets knocked back. They always overdo this in movies with gunfire, right? Somebody shoots their gun and they fly backwards because they shot this big giant gun or something. Same thing here. Okay? Same principle here. It's just it's not nearly the effect that you would think. It is there though. It's not not that it's fake. It is there. It's just overdone in acting. Anyway, let's get to the problem, right? So the before picture shows 0 velocity. The after picture shows 2 velocities. In the beginning, there are 2 different masses. In the end, there are 2 different masses. So what we need to do when we deal with conservation of momentum, as long as there's no friction involved, friction would imply that there is some exterior force that is acting upon this thing, or if there was an impulse, which is an exterior force having a large impact. Neither of those things are taking place. There's nothing that's coming in from the outside environment. There's no friction that's on the ice. So we can go ahead and use conservation of momentum, which means that the change in momentum must be 0. If the change in momentum is 0, we can set it up just like we did in energy conservation, where we can have P final is equal to P initial. Now, the trickier part with this one is you have to account for all the objects. So how many objects do we have in the final? Well, there are 2 that are moving. So in that case, I need to account for both. So I'm going to have M1, V1. This is going to be one of the objects. It's the momentum of one of the objects. Plus M2, V2. So this is whatever the second object is. Now, if I look at the initial, I still have 2 objects. I have a mass of an archer, a mass of an arrow. So I still have 2 objects. So I'm also going to have M1, V1 plus M2, V2. Okay. And now I can start kind of plugging in and seeing where I'm at in this thing. Like, what do I need to still solve for? So I've got numbers and I've got things. Let's go ahead and say that the archer is mass 1. And we'll say the arrow is mass 2. Okay. So that'll help identify some stuff. We always start with the final. So let's look at the final. Mass 1 would be the archer. Well, the mass of the archer didn't change. He's still the same weight as he was before there. That's going to be 60 kilograms. And the velocity in the final of the archer, that is what we are trying to figure out. What is the velocity there? So I'm actually just going to put V1 final. Okay. Takes care of that. Momentum's rather easy because it's just M times V, but you'll have multiple things going on. So it can get complicated quickly if you have multiple objects, lots of objects. M2 is the arrow. Okay, I have the mass of the arrow. And I have the velocity of the arrow. The velocity is traveling in the positive direction at 85 meters per second. Okay. So I have 85. Now I look at the initial. And on the initial side, I have the mass of the archer, right, 60 kilograms. But the velocity of the archer is 0, standing still, drawing the bow back, ready to go. But the velocity is 0. It's going to go to 0. How about the arrow? That has a mass, but same thing. It has not been fired. It's simply ready to go. So the mass there, or velocity there, is also 0, which means this whole side goes to 0. Okay. All right, so now we got a little bit of math to play with. First off, we'll get this 85 multiplied by 0.03. And we'll move it to the other side. So I'm going to minus this quantity over to the other side. So we'll have 60 V1 final is equal to negative 2.55. And then I'll divide by 60 on both sides. That'll get rid of the 60. And I'll have that V1 final is equal to negative 0.04. Okay, why is it negative? Well, it's because the archer is going backwards. He is being flung back, opposite of the direction of the arrow. Okay, so that should make sense. What's the velocity of the archer? If you fire something this way, it'll blow them back that way. If you want to think about it in bigger terms, if this isn't quite making sense, replace the arrow with a cannon, right? Shooting a big giant cannonball. The larger the mass, the larger the velocity, the bigger the influence it has. But you have a cannonball flying this way. You have the cannon giving the what they call recoil back in the other direction. Okay, so same kind of scenario there. Velocity point 0.04 meters per second. All right, that is a type of collision. It's just the opposite. Normally, two objects come apart and they collide together. This is just the opposite. We have two objects that are together that got blown apart. Okay. All right, let's try another example. Example 2. So this one, again, we have a before and we have an after. So we kind of realize, okay, this is a momentum question. In this one, it's a little bit different. We have a car coming in. It's going 15 meters per second, and it's going to collide with a brick wall. Once that collision occurs, it hits the brick wall. The front of the car gets all smashed, crumples up, and it bounces back off of the wall. Okay. The bounce back speed is negative 2.6 meters per second. This collision takes place in a split second, 0.15 of a second. The mass of the car is 1,500 kilograms. Okay, accidents happen fast. First off, what is it looking for? It wants to know what is the impulse that the car felt. And then secondly, it wants to know how much force was on the car. What is the force on the car? Okay, so in this one, we have to look at it and go, is momentum conserved? And we go, well, there's only one mass. The mass does not change, but the velocity sure does, right? It didn't go anywhere. It didn't move the brick wall. The brick wall stayed in place. And it was a very sudden, the time was very small, very sudden change in momentum. So this is all leading you into an impulse, okay? Remember, if it's conserved, the change in P is equal to 0. But if something is not conserved, if it's a not conserved momentum collision, like a brick wall that does not give, will not move, then this is not conserved. In which case, it must be equal, I'm going to put it on the other side. It's not 0, but it is equal to an impulse. And we also know a few things about that. We know that impulse is equal to force multiplied by a small change in time. So all of these things lead to a momentum problem. It states in there, it's looking for impulse, it's looking for force, the very small amount of time. All of this leads to a momentum type problem. So a little bit of foresight when you have to take a test or something. Okay. So how are we going to do this one? First off, it wants to know what the impulse is. Well, this impulse, there's a t involved, but I don't know the force. And since problem B asks for the force, I don't see a way of calculating it. So I'm not going to use this one for the impulse. I'm going to use the other equation for the impulse. Because all that does is depend on momentum. Momentum depends on mass and velocity. I was given velocities and I'm given the mass. So impulse equals change in momentum would be the one I would want to use. So let's start it. We'll go impulse is equal then to the change in momentum. So I have to do P final minus P initial. Now I only have one mass. My final mass is the same as my beginning. It's going to be 1,500. Okay, so I'm doing P is equal to M times V. My final mass is 1,500. My final velocity is going to be negative 2.6. All right, so that takes care of that part. Minus my initial mass, 1,500, times the initial speed, which was 15. Okay, so this is this. Okay. M times Z, that's all it is. M times Z. Okay, well that's just a number. We can calculate that out there. 1500 times this negative 2.6 and a 15. Oops. Yeah, I screwed all that up. Let's go 1500 times negative 2.6. That gives us a negative 3900. And then we minus 1500 times 15. And that'll give us an impulse of negative 26,400. All right. What's the units for impulse? Well, it's just change in momentum. Okay, change in momentum would just be mass times velocity. So we could have kilogram meter per second. That's fine. You can do it that way. We also know that impulse is force times a small amount of time. So you can do it as a Newton second. That's okay too. We can run it like that. Either or is fine as long as you have some units attached to your final answer is all that matters to me. Okay. All right, so there's our impulse. Our impulse I. Now, what is the force on that car? Now that we have an impulse, we can use the second equation, right? That the impulse I is equal to a large force over a small amount of time. The impulse, 26,400 equals to F is what we're going to try and find, and our time is 0.15. All right, so all we have to do is take our number, divide it by the 0.15, and we've got our answer. It is 176,000 newtons. $176,000 newtons is a lot of force. If we, oh, sorry, I forgot the negative sign in there. It doesn't matter. It's we'll just do magnitude of force. So the negatives in there, negatives out of there. It doesn't matter. It's going to be a force either left or right on the car. So why do your cars have airbags and seat belts and all of these other safety features? Is because that is an enormous force that it feels. How does an airbag help you in an accident? It increases, it can't adjust your speed, it doesn't slow the car down, although some computer control systems now will automatically apply brakes and try to slow the car down. So that's one way of just slowing that speed. But during the actual collision, what happens when your airbag deploys? It creates a pillow and it increases this amount of time. That's the whole name of the game for safety features on vehicles and whatnot, is to increase that amount of time and distribute that force out as long as it can. Okay? That's why the front of the cars are known as crumple zones. They purposely will fold and bend and shape to make the collision from the point of impact to actually when it's all fully crumpled and finished, final end move, the most time possible has passed. Okay? If you increase that time, it's being divided over here, so you end up getting a lot better, a lot better chance of survival, a lot less force on everything else that's going on. So that's what it's doing. It's a factor of time, trying to increase time. Anyway, there is 1 and 2, A and B, both done there with example 2. Okay, let's move on to number 3. All right, example 3 is our first example of a completely inelastic collision. We'll use cars because it's easy to picture. Here's our before setup. We have a delivery van or a truck. It weighs 1,800 kilograms, and it is stopped at a red light, so 0 meters per second. Here we have a fancy blue sports car. It weighs 900 kilograms, and it's traveling at 20 meters per second and is not paying attention. It will collide into the back of the truck, and in doing so, the two become one. Okay, it entangles itself in the rear end of the truck and it comes locked in place. And so they go skidding off under the red light, but at what speed do they go skidding off? Okay, Obviously, the one's going to hit the other. You can also have problems like train cars, where a train car will run into the back of another train car and couple, become entangled, and will go off coupled together. Same kind of principle. Lots of things can do that, right? I could have magnets that would all connect together as they had collisions. Same thing. We have one object colliding into another object, and in the end, they become a single object. All right, so we need to look at it and we go, okay, well, what is happening here? How should we go about this? Is there anything about friction? No. So there's no external force there. Is there anything that does not allow the objects to move freely, like a brick wall or something that is stationary that would drastically cause a force? And no, not in this problem. There's nothing there. They're both vehicles. They're able to go ahead and roll around. And you can kind of picture this one in your head that obviously, as the car hits the back of the truck, it's going to give way and give it a push. So we can use conservation of momentum. Okay. Using conservation of momentum, let's see, I'll probably put it, I want to have space. So let me put it here. Change in P is 0, which means, oops, not M, which means that P final is equal to P initial. And because there's no change, that means the final must equal the initial. In the end, let's look at what we have. We have momentum is equal to mv. They're both connected at this point. So what is their mass? Well, they have become one object. An 1,800 kilogram truck and a 900 kilogram car will lead us to a 2,700 kilogram truck car, okay, all together. What is their velocity? Well, that is what we want to know in this problem. So it'll be the V final of the combined pair. How are we going to get there? We look at the initial and we say, well, what's happening? In the initial, I have this little hot rod car, which has 900 for a mass, traveling at 20 meters per second. I also have this big truck, but it is an 1,800 kilogram truck. It is moving though with 0 velocity. Okay, so the second mass, even though it's there, it's still just a 0 because it is not moving. Okay, that looks kind of like a times. That's supposed to be a plus. Plus 0. Okay. All right, well, all we have left now is to just solve out for VF and see what's going on. So I've got a 900 times 20, and I'm going to divide that by the 2,700. And I get 6.67 for my final velocity. So I'll go ahead, I'll add that up to the other side. 6.67 is the final velocity. It's a positive velocity. Well, it makes sense because this car hitting this truck would not cause the truck to go backwards. There's no reason for that. You can kind of see that isn't what's going to happen. So 6.67 in the positive direction makes perfect sense. How about if it flips around? All right. Let's assume this problem, but in reverse. Whereas the car was sitting still at the light, and the van or the truck was the one that was traveling 20 meters per second. All right, if we flip it around, all right, what does that look like? Okay, well, that's just another problem, but we can kind of picture that. Let me get rid of this. Let me say that, let me pop this in a different direction. Okay, there's our sports car. It's not quite the same sports car, but you know, it'll work. So now I'm just going off onto a second part. I'm saying what happens if the two have swapped positions. And this is now the truck that is going 20 meters per second. Do you think I'm going to get the same result? Do you think I'm going to get the van truck mess to be going at 6.67? Some of you might be saying yes. Some of you might be saying no. But now what do I have? I have, in this case, with this collision, I have this, and I have I guess it's still be boxy in the back. But. All right, big crash. They're all messed up now. And now, what is the velocity of those two? Okay, I'd set it up the same way, right? Exact same way. If you were given this problem, you do pi is equal to pf. We look at the final. What is that? It's still 2,700. So it's looking like it's going to be the same answer. 2,700 is the mass. Velocity is the thing that we want to know. We set that equal to the initial. This time, the 900 is 0, and all we keep is the 1,800, which is traveling at 20 meters per second. So that's mv of the initial. And now we plug in, and we see if we get the same thing. Okay, so we get 36,000. We do 20 divided by 2,700, and we get 13.3. Much faster to have the big truck hit the little car than it is to have the little car hit the big truck. Okay. This is why it's dangerous to have a little car and brake check semis, or work with construction vehicles. If those things do collide with smaller objects, they can lead to bigger collisions and faster velocity because they carry more momentum going into the collision. Okay, think about a bicyclist or a pedestrian when they get hit by a car. The car handles the dominance of the momentum. When they collide in with the car, a person is going to all of a sudden get a large impulse on their body and be ejected forward with a high velocity. So anyway, gives you a couple of examples anyway, of types of collisions where they are completely inelastic, where they collide and stick together in the end. All right, let's try something else. All right, so with this example 4, this is one of those problems where you see in every single physics book, you see them show up all over the place on tests and different variations and in homeworks. So this is an important one to go through. It has a lot of parts to it, but it gets you experience and it gets you used to it. So it's a good problem to go through. So what it is we have a projectile here. We have a bullet. It is traveling with some unknown velocity. So it was just fired from a gun is the premise. It weighs 0.1 kilograms, so really, really small, 10 grams. And it's going to get fired into this block of wood. Now that block of wood is suspended from the ceiling by a rope. And it is currently not moving, and it has a mass of 2.5 kilograms. So this is the before. We have a bullet speeding towards this block of wood. So you can kind of imagine what will happen after. The bullet will lodge itself into the block of wood, and it will displace the block of wood on the rope. The rope will swing, and the block of wood will be raised 0.65 meters from its initial position. And the question is, how fast was the bullet? Okay, the original speed of the bullet. So they used to do this in lecture halls, where they would come in with, the professor would come in with a hunting rifle and fire this thing into a block of wood, and students would visually measure it, how high the block of wood went. But that was long ago, days long past. We're going to keep ours all on a whiteboard for today. So let's take a peek at it. We want to find out velocity. It sounds a lot like it should be a momentum problem, and it does involve a collision. It has multiple masses, so it's a great place to start. As far as is it conserved or not, you're looking for, is there a large outside force acting on this? And the answer is no. There's no friction involved. There's nothing coming in that would give it an impulse. It doesn't go into a brick wall or anything like that. So you can use conservation of momentum. Change in P is 0, which means our final momentum is equal to our initial momentum. Okay, if we look at the end in the after result, I'm going to have mass 1 plus mass 2 traveling with some final velocity. Okay. If I look at the initial, I only have one mass that's moving, and that's mass 1, and it's moving with velocity 1. Okay, so the other mass is not moving, so that's not going to show up here in this. And the two masses are combined in the final, so they're going to be combined like that. So hopefully that makes sense from what we had just done in other practices. Okay, so if I start putting some stuff in, mass 1 plus mass 2 is just going to be 2.51 kilograms. Okay, the 2.50 plus 0.01 kilogram for the bullet times some final velocity. Now, that final velocity, you would think, if you bring it up and eventually it comes up to a stop, it has risen up on that string and stopped, that this would be a 0. And if I put that 0 in there, it kills the rest of the equation, right? So if I continue on here, I put the other mass on. All right, so this is my questionable variable, V1, right? If I put this as a 0, all right, it doesn't help me. It says that the VF is 0, so I have nothing in the final. And in that case, then I have nothing in the initial, and I can't have any momentum anywhere. And we know that that's not true. We can see that things are moving. They have velocity, so we have to think about it a little differently. Okay, this problem is meant to challenge you. And the questionable part is we're thinking about the final velocity a little bit wrong. Okay, you break that problem down into multiple steps and do it in multiple things. If we look at this being the before, and really the collision is just when the bullet embeds itself into the block. Moving up on the rope is an after effect, right? If we look back at our previous example with the car and the truck, they had a velocity when they had merged and entangled. They had a velocity that they traveled along with. The same will happen here. It will embed itself into the block of wood, and then it will continue with the velocity. What does it do with that velocity as it continues? Well, it changes into potential energy. It changes into a rise in potential energy. So really, what I want to do is I want to find out what this velocity is, the initial velocity down here, when the bullet enters the wood. Because if I have this initial velocity, that I could put over there as the final velocity for the other half of the problem. Okay, let's take a look at this. Going off of here, if I want to find out how much velocity that block had that allowed it to come up the 0.65 meters, that's just a conservation of energy problem. That's telling me E final is equal to E initial. Okay. No friction, nothing going on there. It's simply changing hands. The energy is changing hands from kinetic to potential. So in the end, I go through all of my energies. I go, well, in the end, it's moved up 0.65. The velocity there is 0. It's got a maximum of 0.65. It's no longer moving. There's no spring involved. This must just be mgy. And the initial, it's all the way on the bottom of the string or the rope. It can't fall anymore. There's no springs. So the only thing that it has in the initial is 1/2 mv squared, kinetic. Okay, now I know both the masses here are going to be the same. It's going to be the 2.51. So they can actually just cancel out. I know that G is 9.8. And I know that Y is the change in height. Now it went from down here to up top, which means this is positive 0.65. And on the other side, I just have 1/2 V initial squared. And that's what I want to try and find here is the V initial. Okay. So if I plug that into my calculator and look at what I got here, I'm going to end up with 3.57 for a VI. Hopefully you can solve out for that now on your own and be okay. 3.57 is the initial velocity at which that block starts to move. This initial velocity is the end velocity over here, which means now I can have 2.51 times 3.57 equals to 0.01 V1. And now I can solve out for V1, whatever the speed was of the initial bullet. And solving that out, I get 897 meters per second. So it's important that you do this one on your own. You do the math, you do all through the works, and you understand where things are coming from. Okay? This one's also very adaptable. You might see it in different ways. One is the easy portion where we just ask, after the bullet hits the block of wood, maybe the block of wood is on a frictionless surface, and I ask for the velocity at which the block slides across the wood. In that case, your answer here would be 3.57. Okay, you've done the middle step. Now maybe in a harder problem, there's friction, and the block stops after a certain point. Then you'd have to find the initial velocity and then use kinematics to find out, maybe what the deceleration was, or maybe I'll have you find the coefficient of friction that was involved in it. Or we can take it to an energy problem where you're looking at non-conservative forces, like a lot of adaptation in there. I can also easily just have it hooked to a spring. And once the bullet enters the block of wood, how far does it compress the spring? I could ask questions like that. Okay, where you go through the same steps, figure out initial velocity of the block, and then set it up to an equality for conservation of energy and see how far it would compress the spring. Or I can have it be all three, right? Where I can have there be friction, I can have this spring, I can have this going up at an angle, I can have a spring at the top that also gets compressed, and have it be some crazy problem that would take way too long to be on an exam. So I won't do that to you. I won't give you something that's crazy. But it's in principle you understand how I can verify the variety of questions, not verify, the variety of questions I can ask about this type of problem. And that then you're prepared. You're ready for whatever happens to be on that exam or whatever problem they're given to you in the homework. Okay. All right, hopefully that made okay sense. That's a tougher problem. It is all one dimension. So let's move on from it. You have one of these, I believe, in the homeworks. And then we'll look at some two-dimension stuff. All right, so let's look at example 5. So two-dimensional motion, or two-dimension momentum. Okay. So here we have a 1,500 kilogram, probably a car, traveling at 25 meters per second, eastbound. Okay. And then down here we have a 2,500 kilogram, probably a truck, traveling north at 20 meters per second. So this is the before. Both cars are traveling. What's going to happen? They're going to collide, crash, mangle together, and we're going to have this 4,000 kilogram wreckage. So 4,000 kilograms because the two cars added together. 4,000 kilograms is going to go and veer off in this direction. So you can kind of imagine that happening. It's going to head over this way. The question's a two-part question. It's wondering what is the velocity of this mess, of the wreckage? What's the velocity? And also, what is the direction of that velocity? Okay, so we have a theta in there as well. And that's the after. Okay, so we're going to have to look at it in a two-dimensional fashion. So again, we have a collision. It's a completely inelastic. The two come together, but there's no outside forces that are in play here. There is no wall or sudden introduction from the outside environment that will prevent you, that would provide an impulse or anything. So momentum is still conserved. So we can use conservation of momentum. Okay, change in P is equal to 0. This then tells us that PF is equal to PI. And because it's two-dimensional, that tells us that we have the P final in the Y is equal to the P initial in the Y. It also tells us that the P final in the x is equal to the p initial in the x. So we got to keep them separate. We have our x's and we have our y's, and we're going to keep them separate. Okay. Well, how are we going to start this one up? So here we've got our momentum. Let's start with the y's. Okay, we've got our p momentum final in the y. We have one mass at that point. So we're going to have the mass, we can use that. The mass is 4,000. It was given in the problem. So I'll jump right into that. I'll say that the mass is 4,000 in the end. Okay, so we'll have that. And then we'll have the component of the velocity in the y direction. So what would that look like? Okay. Well, we have to use our SOHCAHTOA rules. Okay. The portion of the velocity in the y direction, the v, was going to be then the total v, whatever v final is, and then we're looking for the opposite. So it would be, if this is the total v and this is the angle theta, then this is the x component and this is the y component. I'm looking for the y component here, right? So that's going to be the opposite. So that's going to be sine of theta. Okay, none of those. We don't know any of that yet. So this one's looking like it's going to be a tough one. All right. Well, that's all that's happening there. Let's look at what's happening in the y direction initially. All right, we have this car traveling, but it's not traveling in the y. So we're not going to care about it. We only can care about what's happening initially in the y. And for that one, I get a mass of 2,500, and I get that velocity, which is 20. Okay, all right. That side at least worked a little bit better. How about in the x direction? We do the exact same thing, right? I'm going to have 4,000 for the mass. What about the x direction of velocity? Well, that's VF, and that's going to be the cosine of whatever the angle is. Okay? And then that will equal just the mass that's traveling in the x, so that's just 1,500. And then that mass's velocity, which is 25. Okay, so now what do we do? Well, I've got two equations. I've got an x and I've got a y. They each have a VF in them, and they each have a trig function in them. So I only have one thing to do. I have to use a system of equations to answer this, which means I need to solve one of them for VF. If I can solve this one for VF, so I'll have VF is equal to some equation, I can then take that VF and I can plug it into this VF. Okay, let's try that. So I'm going to take this equation, I'm going to take the y, and I'm just going to solve for VF. I want it to be VF is equal to something. Okay? So what do I get on the, sorry about that, dropped my marker. What do we get on this side? We're going to get 2,500 times 20. That gives us 50,000. Okay? So I'm going to have 50,000. That's this. Now I need to divide that by 4,000. And I also need to divide that by sine theta. Okay, so hopefully that makes okay sense. Now I'm going to take this, and I'm going to plug it in down here for that VF. Okay, because I got two unknowns, but I have two equations to go on, so I can make this work. Okay, so if I plug it in for that, I'm going to have 4,000, this 4,000, and then I'm going to have this mess, 50,000 divided by 4,000 times the sine theta. Okay. And then that's for VF, so I also have to multiply this by cos theta. Okay. And then this whole thing is equal to, well, 1,500 times 25, which is 37,500. Okay, I've got multiplying by 4,000 and dividing by 4,000. So I can get those out of the way. Next, what do I got? Well, I have 50,000 divided by sine, but then that's multiplied by a cosine. So I have 50,000. 50,000 cosine over sine 37,500. Cosine over sine, doesn't that seem like something we might know in our trig functions? If I had sine over cosine, that would be a tangent, right? If I had sine over cosine, we would have tangents. That's our trig functions from back in our elementary, middle school area. Sine over cosine is tangent. So if I can multiply this to the other side, flip it over, right? I can do that. I can multiply by sine and then divide by cosine. I can flip it onto the other side. I will have sine over cosine. That's just tan theta. Okay, I can do that. So that means I got to put it onto the other side, which means I'm going to have 50,000 is equal to, and then I'll have tan theta, because I did the flip. And I'm actually going to divide this on the other side as well. So again, just algebra. I'm hoping that we're following along enough at this stage, in this stage of the course, that your algebra is okay enough where we can do that. And now all I have to do is get theta by itself, right? So I need to get rid of that tan. How do I get rid of tan? I do an inverse tan. So that means the tan inverse of this number is then equal to theta. And hey, I've got one of my problems, one of my variables solved, right? I just need to figure out what the inverse tan is, and that's our calculator's job. All right, so let me do an inverse tan of 50,000 divided by 37,500. And it gives me an angle of 53.13 degrees. Okay. 53.13 degrees. All right, now I'm getting close. That's one of my answers. That's the direction. Okay, now all I got to do, now that I have the direction, all I got to do now is figure out what the V final is. Okay? And how do I do that? I go back up to this equation that I made. This already has a V final. All I need to do is plug in the theta, and I can solve for my V final. So that's how I'm going to get V final. Is I'm going to take that equation. I'm going to do 50,000 divided by 4,000. And I'm also then, either I need to put brackets in where I can have sine theta, or I need to divide again by sine of 53.13. All right. And that gives me a total of 15.63 meters per second. Okay. So this one's tricky. It's got some trig, it's got some math, it's got algebra. You're using systems of equations. This one's definitely a little math challenging for you, but hopefully that made sense. Okay? At least you can work it out on your own, I'm hoping. Okay. So we got 15.63. So after all of this is done, I'm just going to write them over here so they're nice and clear. This is always the best for grading, is when you have a nice, concise answer. It makes it easy to grade, and that's where you get all your points. So 15.63 meters per second and 53 degrees. Does that make sense? 15 meters per second, would that be about right? Two vehicles just got in a wreck. I don't think they're going to speed up by getting in a wreck, right? They're both probably going to end up slowing down. It's going to take some of that speed away because now they're much heavier. So yeah, I think that works out okay. All right, see what else we got. All right, last example. Example 6, we'll do some center of mass problems. So I wanted to do one that was two-dimensional. Just give you a good idea on how to do these problems. They're not too difficult, I don't think. I think they're pretty simple problems. So we'll do one example of it. Hopefully you'll see where we're going with it. We have the equation written up for the x center of mass. This also works for the y. You just have to change all the x's to y's. Same with z if you wanted to do it in the z-axis. Here we have a 3-mass system. We have mass 3, which is 2 kilograms, and then mass 1 and 2 are only 1 kilogram. Mass 1 and 2 are located on the x-axis. Mass 3 is located on the y-axis. And the question is, if this was a solid mass, where would be the center of its mass? So like the balance point for it. Okay. And it's not always on an object either. You can have collections of masses that just don't balance. There's just no balancing point. Okay, so don't expect something to be on the masses. And it's if those 3 masses were to stay in those positions and the outer sheet just holds them all in place but is massless. Okay, anyway, let's take a peek at it, make some sense out of it. So being that this is already written for the x position, I'm just going to go ahead and do the x position. So I want to find the x center of mass. Okay, well that's equal to the mass of M1, which is 1 kilogram, times the x position of mass 1. That's located at 1 meter. Okay, easy enough. Mass 2, well that's also 1 kilogram. Mass 2 is located at 2 meters along the x-axis. And then finally, we do have a third mass. That mass is 2 kilograms. And where is it located on the x-axis? It is located at the 0 point. Okay? So it's going to go to 0 anyway, but it's fun that we did include it. We do have to include it in the bottom where you add up all of your masses. This is still a 3-mass system, so I need to have mass 1 plus mass 2 plus mass 3. Okay, it still counts there. It's still part of the system, so I have to include it. Okay, so what do we get here for our x center of mass? Well, 1 times 1 is 1, 1 times 2 is 2, 2 times 0 is nothing. So I end up with 3 divided by 4, or 0.75. Now this is only in the x direction. I have found half of my problem. Okay? I have found out where in the x-axis the center of mass lies. But this is two-dimensional. I also need to do this for the y dimension. So let me do it again for y, the y center of mass. All right, so now all I have to do is do it all over again. Mass 1 is still 1. But the y position is 0. Okay, they're on the x-axis, so they're on the 0 part of the y-axis. Same with this one. I'll have 1 kilogram, but I have a 0. The only one that is on the y-axis is the 2 kilogram mass, which is located at 2. And then we'll divide by all of the masses, which we already know is going to be 4 from up here. 1 plus 1 plus 2. So I've got 1 times 0 is 0, 1 times 0 is 0, 2 times 2 is 4. This gives me 1 in the j direction. Okay, so where is my center of mass? My center of mass is then located, so we could just go as CM, center of mass. My center of mass is located at 0.75 I hat plus 1 j hat meters. All right, so that's where the center of mass lies. Where is it on our drawing? Well, we just go to those coordinates. 3/4 of I, and then we go up 1 in j, in the x. That's roughly our center of mass. That's our balance point. Okay, so it's not on a mass, it's just out in the open. Okay, you'll have one of these that's on the homework as well. May seem a little bit tough, but there's a video as well online for it, so hopefully that makes okay sense.
All right, that'll wrap up the examples here for Chapter 9. We'll see you back for Chapter 10.